I want to end this Verilog primer by talking about an important concept called hierarchical Verilog code. Actually, it's hierarchical design. So let me just explain it using an example. So in this example, we will build a 4-to-1 multiplexer. So now I did increase the number of inputs as opposed to having just 2 inputs. Now I have 4 inputs, and because I have 4, I would need a couple of bits for the selector. So it's a 4-to-1 multiplexer. Of course, we can go and write the truth table, and that truth table will have 1, 2, 3, 4, 5, 6. So basically we'll have like some 6 signals, A, B, C, all the way here, and you have one output. So it's a signal that takes, or it's a circuit or a combinational circuit that takes 1, 2, 3, 4, 5, 6 inputs and gives me one output. You can write the truth table, and of course there's like 2 to the power 6 cases, and it's a pretty large table to do by hand. However, you can definitely do it, and I trust that you can do it easily, or you can even go back to your old digital logic notes and just figure out how a 4-to-1 multiplexer is implemented. However, this isn't what we're doing in here, and as it turns out, in design in general, what you do is you usually build something a little bit smaller that does the function, and then you build on top of that. And that's exactly what we're going to be doing in this hierarchical way of design. So what I will do is I will use the 2-to-1 multiplexers that we designed. We have a bunch of them. Actually, we designed a few different designs. Actually, they're all the same. They function the same. They're different in the way they operate, or the way we wrote it, but they function the same. So I'm going to use a bunch of these to build something larger. Please note that this is really, really important in digital logic. It's a common theme that you will encounter throughout not only digital logic, but any design in general. Usually you design something simpler, small, like manageable, and then you build on top of that by combining a bunch of these together, and it makes your life a lot easier. So what I would encourage you to do is to pause the video and try to implement the 4-to-1 multiplexer using a bunch of 2-to-1 multiplexer. Figure out how many you need and then go from there. Okay. Hopefully you actually did pause a little bit before you actually looked at the slides or looked at the next one. But really, in fact, this is one way to do it, or one way to implement that particular 4-to-1 multiplexer. And what I did in here is I took 3 of these 2-to-1 multiplexers, okay, and I just connected them together, and I built a 4-to-1 multiplexer that way. Okay, so let's see how we can actually implement this in Vivado or in Verilog. So I'm going to go to Verilog, and I'm just going to implement that in here. So let's see that. Okay, so we have that now. What we can do is we can just open a new source file. So we're going to do this here. We're going to create that file, and then I'm going to say, well, it's a mux, and it's a 4x1 for now. I'm not going to describe whether it's behavioral or structural. It's actually kind of neither. We'll see. Okay, so we're going to say okay. We're going to say click finish, and now what we have is we can of course input all these inputs and outputs in here, but what I'm going to do is I'm just going to say yes, and I'm just going to go write it myself. So let's see what type of inputs and outputs I have. What I usually do is I'll come in here, and that's the circuit diagram that I have, and I'll just draw a big square around it, and I'll figure out my inputs and outputs. In fact, speaking, this tells me that from x0 all the way to x3, their inputs, actually S0 and S1 are input 2, and I also have an F as an output. So I'm going to just do that. So let me just do this in here. That is the one that is a 4-to-1 multiplexer. I'll close that design in here. Okay. And then I'll close a bunch of these designs in here just to clean up like my workspace a little bit. So we're going to close that. Or actually, let's keep them open. Let's keep these open. That's fine. Okay, so we do that 4-to-1 multiplexer. So how do we write them? Well, first I'm going to start by my inputs. My inputs, I have input x0, x1, x2, and x3. Okay, and I have also an input which is s0 and s1. Of course, you can put them as a bus if you want to, but I'm just going to keep them that way. It's simpler. And then we have an output, and it's f. And we'll figure out whether we need to register it or not in a few seconds. Okay, so how do I go about this one in here? We have written a few modules, a few Verilog modules, and every single time we'll put the input and output and we just write code in here. But if you take a look at this design in here, the one that we have in front of us, you will see that really we have this one here is implemented already, and I have this one here implemented already, and I have this one here implemented already. And as it turns out, a box can contain other boxes inside it, and that's why we call it hierarchical design, because you can design a module. You can, for example, pick up any of these 2-to-1 multiplexers and just utilize it in a different one. Okay, and that process is what we call an instantiation, or creating instances of a module. So let me show you how we can do this. Well, according to this diagram, I need 3 2-to-1 multiplexers, 1, 2, and 3. Okay, so what can I do about it? Well, you can pick up one of these ones that we designed. Let's assume, for example, I'll just use the gate level one. So I'm just going to open it in here. Let me just do that in here. Okay, we'll open it on the side. All right, and well, you probably won't see it. So let me just see if I can open it in a different way. We'll open it this way here. Okay, hopefully you get to see it. So that's basically it, and that's the other code in here. So I have the 221 at the bottom and the 41 at the top. So how do I go about it? Well, here's how we can instantiate a module within another one. Okay, in hierarchical design we do this instantiation, and this is, I want you to think about it as the following. You have a multiplexer and you want to use it. So what you do is you create an instance of it, and that's how we go about it. Look. So what I do is I say, well, I need a multiplexer that is 2, 2 to 1. And I'm using the gate level one, so I'm just using that. You basically use that name in here. And I need 3 of them. But for now, I'm just going to start with the first one. And let's say that this is the first one in here. Okay, and what I'm going to do is I'm going to call it M0. Okay? Okay, so I'm going to call it M0, and as it turns out, that name is mandatory. It's not gates anymore because we're creating instances, and different instances of the same thing might be confusing to Verilog, so you're going to have to give it a name. I just gave it the name M0. Okay, so that name M0, well, of course, I have to tell it what's its inputs, what's its outputs. So how do I know this? Well, I'm going to take a look at the definition of the module in here. It's expecting X1 and X2, and then S, and then the output at the very end. So what you can do is you can say, okay, I need X0 as the first input, X1 as the second input, and then which S am I giving it? Well, I'm giving it S0. Okay, that's the selector, and which output it is? Well, I'm just gonna give it some sort of a signal name, and let's call it, for example, G0 in here. Okay, and you can say G0. And usually what I do is I go in here and I define these just in case. Okay, you don't have to do it if it's a one wire, or it's a one signal. It's not a bus. But I usually do it because it's a good style. All right, so we did this. That's perfectly fine. So we have utilized, or we have instantiated or created an instance of that multiplexer. This process is called instantiation. However, we're not done. We need more. Okay, so we need 3 more as well. Okay, so what I'm going to do is I'm going to say I'm going to create another instance of this 2 to 1 multiplexer. Okay, so I'm going to do this here, gate, and I'm just going to name it M1. And that would be my M1 in here. Okay, so this is M1, and I'm going to call its output as G1. Okay, all right, so that's M1, and again, I can give it that in order. So the way that I have ordered it in here, and that's the reason why I opened that design in here, because I needed to know the order, and this is what we called these are ports, and we're connecting ports together. We're connecting like wires to ports. So this is what we called ordered port connection, because it's based on the order that you define them. Now, if you go to this code in here, and for some reason or another you needed to change it, and you inserted, like, for example, another word in here, and you decided that you need another input, and that input you called it, for example, FFX or something like this, and you did this, your code here would break, okay, because it's based on the fact that this is never changing. So this is not really good programming habit. So what we do is we have a better way to do it, and that better way is what we called a named port connection. And in a named port connection, the order doesn't matter anymore. So let me show you how we do this. Usually I do this here, and then I open it, I create a new one, and then what I do is I say, okay. So what you do is you say, all right, I know that I have a signal called X1. So I'm going to say dot X1, and now I'll figure out which one I'm going to connect to it. That X1 comes from here. Okay. I know that there's another signal called, again, the order doesn't matter, S. I'm changing it on purpose here just to show you. Okay, and I know that I need another one, which is X2, and now I know that I have an output that is called F. Frankly speaking, I can start with the output at the very beginning. It doesn't matter, the order doesn't matter. So what I'm going to do is I'm going to go in here, and I'm going to say, well, dot F in here, and then here's a comma, and of course the last one, we're going to have to remove that comma. Okay, so what happens in here? Well, I created an instance, or I instantiated an instance. I called it M1, and I said, well, it has an F, it has an X1, it has an S, and it has an X2, and I need to connect things to it. I didn't yet. Okay, so let's see, what do I need to do? So what I need to do is in here is I'm going to take a look at my circuit in here, and I'm going to say, well, the output is F, and I need to connect it to what we call G1. So I'm going to say, well, connect it to G1. And of course, because that's a new wire, I'm just going to say G1 in here. Okay, what about X1 in here? Well, The x1 is nothing, it doesn't have to do anything to do with that. It's the x1 of the 2 to 1 multiplexer. What's the x1 in here? Well, I have x1 and x2, right? Yes, I have x1 and x2. Well, x1 is that one here. I'm going to connect x2 to it. Okay. And then what I have is for the x2, just so that I don't get confused, it's actually x3 in here connected to it. Okay. And what's connected to the selector? It's actually s0. And now this emphasizes the importance of having a diagram before you actually started programming. So a lot of people and a lot of novice programmers or novice Verilog coders, they will just go ahead and try to write code without actually having something in front of them. I usually start by writing something on a paper and I just follow it exactly like I'm doing right now. It just makes your life a lot easier and you can track your code a lot faster. Okay, good. So now we created a couple of instances, M0 and M1, but I still need another one. And as you can see, I'm not copying and pasting that code of the 2 to 1 gate. I only have to create it one time and that's it. I'm creating instances of it. Think about it as functions in C and you just reusing that code. Here we're reusing hardware description, okay? Or we are reusing modules. You don't have to copy and paste it. Okay, so how do we go about it? Well, I usually would go in here and I say, well, I have another multiplexer. It's also a 2 to 1 and it's also gate. And then I'm going to call this as M3. And then I can do the same exact thing. I usually do that named port connection. Okay, and I say, well, I have, and I usually go with like something more logical than what I did before, but in terms of order, okay, x2, okay, and then I have .s, which is the selector, and then I have the .f, and then I connect something to it. For example, I know the x1 in here, you see this is my x1, I know it's connected to G0. You see how convenient it is to have it on the diagram. And now this is my x2, it's connected to G1. Okay, so I'm going to say G1. And now my selector in here, let's see what's connected to this selector. It's actually connected to S1, the external S1. And then in here, which is the F, is going to be connected to my signal F, which is that one in here, that output. And now I believe my circuit is done. It's complete. Do I need to do register? Frankly speaking, no, because I'm not using any always statement. Okay. One more thing before I actually go and see if actually it implemented it correctly or not, whatnot. So what I want you to see is the following. Like I instantiated M0 and then M1 and followed by M3, but I don't have to do that. I can actually do this M3 before any of them. Okay, you can just do this here. Okay, I instantiated the third one, which is the one closer to the output before the other ones, because it is Verilog, and the order of these, because I'm not within an always statement, the order of these gate or instantiation doesn't really matter. Okay, so let's take a look at this RTL analysis. But before I do, I just want to go and take a look at my sources pretty quickly, and I want you to see one thing. So we have this multiplexer 4 to 1. Okay, that's the source code. If you actually go run the analysis, it will take the other one, which is the behavioral, because that's the last one we dealt with. So you need to make it a top file. And now it will make more sense why we call it top file. We call it a top file because it usually is the top file. Look, it's a top file, it's a 4 to 1, and we created 3 instances of the 2 to 1, and one is called M3, the other one is called M0, and then M1. Like the way they're listed here is exactly how they're listed in the code. Okay, and that's why we call it the top file, because, and this is this little icon of it. It's basically, it's a module, and there's under other modules or other files as well. And this is why we call it the hierarchical design or hierarchical code. All right, so let's take a look at this one in here. So I'm going to just call it here. I'm just going to save everything, and hopefully it will interpret it as a 4 to 1 multiplexer. Okay. Okay, so what did it interpret it as? Well, let's take a look at it. Well, it didn't interpret it as a 4 to 1 multiplexer, but what it did, it interpreted it as 2 to 1 multiplexer, 2 to 1 multiplexer, 2 to 1 multiplexer, and you can actually internally, you'll see it actually interpreted it as the gates, because what I did is I used the gate level modeling. So it did not use multiplexers in here. Probably that's why it couldn't see it as a multiplexer or a 4 to 1 multiplexer. But anyway, it interpreted hopefully like I expected it to be. Okay, before I close in here, I just want to make sure that you understand that we don't have to use the same exact gate level modeling in here. Meaning, I needed 3 2 to 1 multiplexer. Let's take a look at this diagram very quickly. So I needed 1, I needed 2, I needed 3. They don't have to be the same exact implementation. You can use the 3 different implementation. In here I use the same one just to show you that you can, but I could have just used the behavioral one. So let me just do this here. I usually open it next to each other, and I just do this here. So that's the behavioral, that's the 4 to 1 multiplexer, okay? So for example, let's say the M3, I'm gonna use the behavioral implementation of the M3. So I'm gonna just say, okay, instead of being the gate one, I'm just gonna use the behavioral, okay? And the signal names are the same, they're X1, X2, S, and F, and I don't have to change anything. So let's take a look at that. Now this one is using the behavioral, and let's keep this as the gate, and let's do this as the data flow modeling. Okay, so M1 would be the data flow. So I'm just going to do this here. I'm gonna say data flow. Okay, and now I'm creating basically 3 instances, like, or each instance is from a different module. And let me just see, it's called X1, X2, S, and F. So they're the same exact names. We do this here, and I'm just gonna reload, and let's see what we'll interpret it to be. Well, it kind of looks similar to what we did before. We have M0, M1 followed by M3, and if you expand that M3, it actually is a multiplexer. If you expand this M0, it's actually the gate level. And if you expand this one in here, it's actually another gate level. This is the data flow one. Okay, so that's neat. That's hopefully exactly what I expected it to be. Or this is what I wanted you to know. So what we have done in here is we use hierarchical design to do this. And I just showed you, let me just take a look at the code. I just showed you that you can create a module out of other modules by instantiating instances of the sub-modules in there. So I have a big circuit in here that's a 4 to 1 multiplexer, and I used 3 in this particular code. Now the last one, I used 3 different 2 to 1 implementation. Vivado doesn't know that they're different or that they're exactly the same, they perform the same functionality. For Vivado, they're different modules, but we know as humans that they're 2 to 1 multiplexers, all of them. You can use all the same implementation or others. And then we saw also the named port connection and the order port connection, which is this one in here. Well, can I test this on the board? Of course you can. Probably you have been seeing all these error messages that I'm getting, and these error messages that I'm ignoring are basically from the sources. It's telling me my constraint file in here has a bunch of switches, because this is from the buffer example that we've done previously in a separate video. You just have to connect the switches together. So if you take a look again at the multiplexer in here, or the 4 to 1 multiplexer, I'm expecting to have 6 inputs and 1 output in here. Okay, so you're gonna have to change that constraint to have like 6 of the switches connected to the different inputs and 1 output connected to F, or 1 LED connected to F.